Ananya, am I audible?
Yes.
Okay. Can we start?
Yeah. So, good afternoon,
Welcome
everyone.
to
Yes.
welcome to online short-term course on powertrain converters in multi-click and vehicle technology. Day 3, session 4. This is a tutorial session will be handled by Ananya Biswal, research scholar from Department of Electrical Engineering, National Institute of Technology, Rourkela. I welcome Ananya Biswal to hand over the session.
Thank you, Vaza. So, good afternoon, everyone. I am Ananya Pritilagna Biswal. My research project is based on SVPWM based 3-level inverter for various applications. So, a 3-phase VSI is best way to provide the variable voltage and variable frequency through AC drives. To get the variable voltage and variable frequency supplied from inverter, various pulse width modulation techniques systems are used, like carrier-based sinusoidal PWM, space vector PWM are the most practiced PWM techniques. Generally for a 3-phase voltage source inverter. Because of easier digital realization and greater DC bus power usage, space vector PWM is now becoming more popular and practiced for controlling voltage and frequency for efficient control technique. This work emphasizes on implementation of SVPWM on an induction motor in step-by-step method. Space vector technique is used to discuss the model of a 3-phase voltage source inverter. MATLAB or Simulink is used to create and simulate the simulation model of space vector PWM, and it is further fed to the induction motor. So here some of the key points I'm going to discuss. So let me introduce you to my topic. These are the basic block diagrams of my model. That is, I have done the closed loop control. So in the open loop control, the SP pulses from the SVPWM fed to the multi-level inverter, and through the multi-level inverter, the induction motor is fed. So in closed loop control system, the speed sensor senses the speed, and we control that speed and again feedback to the SVPWM block. That is the basic block of my model. So coming to different techniques. The purpose of various PWM based technique is to reduce the current's total harmonic distortion. Increasing switching frequency reduces the lower harmonics. Required output voltage with the reference value of frequency and RMS voltage, which also leads to the sinusoidal waveform generation. The sinusoidal PWM is the most common. Even though it is widely used, it has a significant disadvantage. It has low output voltage as compared to the PWM techniques. However, employing comparable carrier-based systems in various configurations, there are also some additional approaches. So, yes. So this multi-level modulation strategies, that is, we can say 2 types: fundamental switching frequency and high switching frequency. Based upon fundamental switching frequency, the 2 types of control techniques, that is space vector control, and C, that is the selective harmonic elimination technique. And based upon high switching frequency, There are various several techniques, that is sinusoidal, trapezoidal, staircase, step, third, harmonic elimination, and SVPWM. So, trapezoidal modulation technique is a reference wave, and a trapezoidal wave are compared for getting pulses. In staircase modulation, the modulation signal is turned on like a stair with the labels calculated to remove particular harmonics. But in this case, cycles fewer than 15 pulses are not advisable. In step modulation, each step is a specific time period that controls the amplitude individually and is used to eliminate harmonics. But still, it has considerable distortions. And coming to third harmonic injected PWM, similar to SVWM, but the reference signal is not a sinusoidal wave. It is made of a basic component that harmonic elimination number is 3. This strategy results in increased amplitude and improved DC source usage. So, SVPWM, these are some of the basic advantages of this SVPWM, that why we are going for SVPWM rather than any other techniques. Space vector modulation has now become a standard for switching power converters, as all of us now know already this. And the PWM is would be said as a better technique for PWM generation in terms of better utilization of DC bus power, efficient switching, and minimum current ripples, which causes the total harmonic distortion to be low. So space vector concept is generally comes from that rotating magnetic field, that is rotating MMF concept, that presenting three variables by a single vector. It is the most useful application, as there is no need to deal with three different quantities in three different phases. Instead, we can represent it in a single quantity. That would be also easier to visualize, and also a single quantity is with less complexity. So basically, it's we can say that it's a mathematical tool rather than a physical quantity. So as I earlier said that there is increase in RMS output voltage by 15%. Rather than SPPWM technique, and extremely simple and straightforward physical implementation, we can say, in a digital processor unit. And it can be implemented with few microseconds and with suitable outcomes. So this is comparison technique of different types of labels, that generally we go for 3 labels, but nowadays many research papers are also been published like 5 labels. But the suitable technique is that 3 label, what I implemented in my work. As the number of labels increases, the layers of the hexagon gets increased. So that is the basic idea behind this multi-level approach. So, the concept behind the rotation of space vectors. As shown in the waveform, that three-phase sinusoidal waveform. So, as it is shown at the 0 instant, the red one is phase A, the blue one is phase B, and the black one is phase C. As it is shown at the instant, the red one, that is the phase A, is at maximum at the peak level, whereas in the phase B and C are at negative. So here the first instant I have taken at omega t equal to 0, the phase IA is in the direction of in its conventional direction of IA phase. If you remind that 120-degree displacement diagram that represents A and B, the B phase is negative and it is opposite to the conventional direction, and it is the negative, and hence similar situation with C, it is also in the negative direction. So the resultant vector will also be along with the A vector, A direction, that is IR. IR is the resultant vector. So similarly at instant of 60 degree, that is pi by 3, here also we can say the phase A is at positive and phase B is also at positive, but phase C is at the negative peak. So the conventional direction of the phase C would be like this, but as it is positive, hence the resultant will also be in along the C axis. Please mute yourself.
Madam,
Anyone has unmuted
yes.
their mic, I guess. Thank you. So now coming to 120-degree interval, these three vectors here IA is at negative. That is that's why it is opposite, and IB is also negative, and IC is positive. That's why the resultant will be along the IB axis. And omega t equal to pi instant, the IB is positive, IC is positive, but IA is negative. That's why the resultant will be along the IA axis, that is the negative IA axis. At omega t equal to 4 pi by 3 instant, IA is negative, IB is also negative, but IC is positive. That's why the resultant will be along the C axis. And here at last, IA is in positive direction, IB is negative, but IC is positive. Hence, the resultant will be in B direction. So, as I said, these are the formulas. By applying, I have calculated the magnitude. Let's consider at instant at a given instant, that is 100. 100 switching state I have considered. So VA.
Madam, your PPT is not visible. Hello.
Yes.
PPT is not visible, madam. Your only voice is coming.
Maybe the problem is from your side, sir. It is visible from our side.
It is visible, sir.
It is visible to us.
Yes, now visible, sir.
Thank you very much. Ananya, please continue.
Yes.
Can you make
So
full screen?
yes.
Can you make full screen? Yes. Okay, continue.
I did. So VAO is will be equal to VD as this is 1, VBO equal to 0 as this is 0. I have considered 1 0 0 state, and VCO will also equal to 0. So VAN, VBN, VCN, with applying these formulas, I have calculated the magnitude as 2/3 of VD. VA will be 2/3 of VD. VB will be minus 1/3 of VD, and VC will be minus 1/3 of VD. And similarly, resultant vector is also calculated, that is 2/3 of the VD. Here, the vector, as it is shown, the vector 1/3 of VDC. As in the previous slide, I have explained that from omega t equal to 0 to omega t equal to 5 pi by 3, it rotates in anti-clockwise direction. So here, if we observe that rotation, it forms an hexagon. Like the switching states, there are 8 states, 1 0 0, 1 1 0, 0 1 0, 0 1 1, 0 0 1, 1 0 1. Like starting from, and 2 0 vectors are at the center, that is 0 0 0 and 1 1 1. Starting from V1 till V7. This the application is mainly on our inverter, that is shown here. For each PWM cycle, space vector PWM creates proper gate drive waveform. This inverter is viewed as a single device that can transition between different states according to the number of switching states. For each state, SVPWM gives distinct switching time computation. This technique works almost with all types of multi-level inverters and can be easily adjusted to greater levels. The duty cycle time also for each of the 3 vectors, that will as here you can see forms and triangle. So here I have considered the 2-level inverter. It contains 6 identical switches, that is from S1 till S6. So which is represented by the IGBT switching devices. The output signals will be represented, and inverter will also produce distinct outputs depending on the switching combination. That will result in a 2-level signal. Here, that is the summary. I have put in a table format that I derived from these equations. With corresponding to each switching states, I have mentioned the vector name, magnitude, along with their angles, according to which they are rotating in the hexagon format. If we if we connect their peaks, it will look like an hexagon. Now coming to switching timing calculation, here we go through the voltage second balance approach. So by voltage second balance approach, the BR is the resultant and TS is the total switching time. And V1, the T1 is the timing corresponding to V1, similarly T2 with V2 and T0 with V0. Like if we do that voltage second balance, we will get these equations. And here from the triangle, if we select this part of the hexagon, it looks like a triangle. And here I have highlighted it, V1, V2 and V0. Here from the triangle, the V reference will be like this, the resultant. And here we have to calculate the each timing sequence, that is T1, T2 and T0. So here we can apply the similar triangle concepts, similar side. So that's why from this we get the T1, T0 and T2. T1, T2 we got, but T0 is nothing but Ts minus T1 and T2. Here the switching diagram. The switching diagram is divided like in eight sections. The starting one is T0 by 2, then T1, T2, corresponding to each switching states. On the output waveforms I have presented, like and T7, T0 are the zero vectors. As I already told, that 0, 0, 0 and 1, 1, 1. So these are the zero vectors. So here the VA0 waveform, we can see this will continue till from T1 again to T1. So after that V0 will again start from T2 to till T2. Similarly for VCO. That's how we are getting the pulses for each switching of the inverter. Again, I have put that all these things in table format. So here coming to the basic model, that what I have done. I have fed that from this three-phase supply, I did the Clark transformation, that I have converted to alpha, B ABC to B alpha beta. So after that conversion, I did the sector identification, that I am going to explain in MATLAB also. So after that sector identification, the switching pulses for each instant are generated. Then again that pulses are applied to the voltage source inverter. So that after this, from that I have fed to three-phase induction motor. So here, as I have taken the induction motor drive, that is, I have implemented with variable frequency control. That control, I can say that different of different types. Variable speed of motor above rated speed can be controlled by different techniques, like PWM technique will give the increased frequency. Increase in frequency, that means synchronous speed will be will be increased. No change in starter voltage is required for that frequency. And air gap flux and rotor current will also decrease. As a torque developed, torque will also be reduced with the variable frequency technique. So that's why I have gone for V by F control. So the variable frequency control, that is two types, scalar control, vector control we also perform. Under scalar control, that VYF control is there, and torque control. With vector control, field-oriented control, or direct torque or flux control, we can also implement. That is the VYF control scheme. I have did with my model that after generating that pulses from by SVPWM technique, I fed to the inverter and hence to the motor. And from the motor feedback, I fed back the speed reference and calculated. This is the block diagram of open loop. Later, I'll go for closed loop. So, with frequency command, then I have fed it through a frequency limiter with flux control. Then again to the SVPWM block. As I told in the previous slides, I did that Clark transformation. That is, three-phase quantities are converted to three-phase reference frame into two-axis orthogonal stationary reference frame using that Clark transformation. These equations we require for that transformation. Here I have gone for my multi-level inverter, and I have gone with the three-level inverters. So multi-level, why we go for multi-level inverter? Obviously, reduce harmonic distortions as the output will be more towards sinusoidal. dB by dt will also be reduced, so voltage stress will also be reduced. Common mode voltage will be smaller, so stress on the drives will be hence reduced, and it will current at very low distortions. So it can operate as both at switching frequency and fundamental frequency. Here, by this, we can also go for reactive power control and selective harmonic distortions. By C technique, will also be the TST can also be reduced. So types of there are three types of multi-level inverters. Diode clamp, that is the NPC, neutral point clamped inverter. Second one is flying capacitor type, and S-bridge cascaded type. I have opted for that NPC, that is the diode clamp inverters. No doubt it has various applications like high to medium voltage level of motor drives, high voltage DC, and for our flag devices. Also, with that, our filtering will be easy, so that cost will also be reduced. And the main utilize of this is nowadays for the renewable energy systems. As the demand in solar and wind increasing day by day, this is the main utility interface we can use for our renewable energy systems. I can say the most important use of application of inverter. So here is the circuit diagram of diode clamp multi-level inverters. So the voltage, two voltage, this is the VDC, the voltage source, and VC1, two capacitors are connected. So two different voltage labels we can get, so that our output will be three level. That is VDC by 2, VDC by 2, and 0. So for K level, like if I generalize for K level inverter, it will require 2K minus 2 switching devices, and K minus 1 input voltage sources. Here, the disadvantage with the diode clamp multi-level inverter is need of high voltage diode to block that reverse voltage. So that will ultimately increase that cost, and circuit complexity will definitely increase, as it is shown already. And but advantage is our output waveform most desirable. And high switching we can also operate at low means not so high switching frequency by using these converters. Here all the switches are identical, and for that like SA1, SA2, SA3, SA4, all the switches will be identical switches. And now I have compared also and I observed the differences between inverter, no, conventional inverter and multi-level inverters. So conventional, obviously, TSD will be low, reduce switching stresses, and high voltage application with higher voltage levels, and with levels will be also be increased, like 5 levels, 6, 7 level, starting from 2 level. dV by dt will also be decreased, and this control scheme, that will be the disadvantage, that complexity will be more. So switching states, that I have considered one leg of that NPC. Here I have highlighted with red color, that S1 and S2. Through this, the current will flow, and hence the VA of voltage will be V D by 2. And here at that instant, S1 and S2 are on. For this instant, the diode, the current will flow like this. Here, the S2 and D5 and S2 will be made on. But here, the voltage will be 0. That is VAO will be 0. At it will sort that part. And here the current will flow like this. These are all the cases of positive current, that is I will be greater than 0. Here the devices D3 and D4 will conduct. Here the cases I have considered of negative current. Here the current will flow from here through D2, D1, and will go to the source. Here voltage will be VD by 2 only, but here the D1 and D2 will made on. And here at E instant, again the current will be negative, but voltage will also be 0. But the switching devices are on S3 and D6. Similarly, here current will be negative, and it will flow through S3, S4 till VD. So now I'm going to do with the MATLAB tutorial.
Ananya, have you struck?
Yes.
Oh, did you open anything?
Is it visible?
No, your PPT slide is not visible.
Okay, okay. Now is it visible?
Yes, yes, you are visible now.
So this is the
Ananya,
yes, yes. I think some problem. Give me 1 minute.
sure.
If the screen is fluctuating,
No, it is visible now.
huh?
It is visible now.
Okay. So this is my MATLAB model for the SVPWM. SVPWM signals here. B reference I have taken 230, VDC I have taken 400, and this is the TS. And with that, I have generated the timing sequence from this sinusoidal wave. First, I have generated that angle. From angle, I have calculated each sector. Here, 5 sectors is calculated. One, two, three, four, five. 5 sectors have been calculated. From that sector, again we have fed that sector an angle and calculated T1 and T2 as I have shown in my PPT. These equations, T1 equal to sine pi by 3 minus theta VR by VD into root 3 TS. Similarly, T2 equal to sine theta VR by VD root 3 TS. From those, T1 and T2 are calculated. After by these functions, here I have written that formula and calculated T1 and T2 and again T0. Then here I can show the waveforms T1, T2 and T0. Then here by multi-port switches, I am generating the signals that first I have made that T1 plus T2 plus T0 by 2 and T1 plus T0 by 2 and T2 plus T0 by 2. Hence the switching this will be like this by comparing the waveforms are generated. Again, here by SVPWM technique, after these signals are generated with comparison with our carrier signal, the pulses are generated. Here, this one is the larger. Then, as I already described in that PPT. Here, the first one is larger. Then again, the second one is comparison to that VAO. VVO is pulse for VVO is of lesser duration, and VCO is again of lesser duration. Similarly, I got these pulses. Here, this is the my after generation of SVPWM, I have fed into that 3-level NPC inverter. This is the 3-level NPC inverter. I have already described in that PPT the 4 switches and 2 diodes and how the switching occurs at every instant. Here, the voltage levels, as you can see, multi-level in form of multi-level sinusoidal. I have generated for 3 phases, phase A, phase B, and phase C. And here, these are the current waveforms for phase A, phase B, and phase C. The load side voltage. That is my final model. Yeah. First, from VA, VB, VC, I have calculated alpha, V alpha, V beta by the equations already shown in PPT. These are by Clark transformation, I have calculated V alpha beta from VAVC. So now after I have calculated alpha beta. Now by alpha beta, I am generating pulses. That is again, I have go for this. I go for that sector, means T1 and T2 timing sequence generation. After timing sequence, I went for sector selection, and again from that sector, the pulses are generated. Like this. Now after generation of the pulses, again I have fed it into the 3-level bridge inverter with two sources, 2-level voltage sources. Now again through the inverter, I fed into the induction motor. So here are the motor variables: stator current, stator currents of 3 phases, that is A, B, and C. And hence torque and speed characteristics are also observed for this speed. The characteristics. Now the rotor speed and electromagnetic torque characteristics are also observed. From the speed, I have implemented that VYF control. So on the speed again by this with I feedback again into that VA, VB, VC. So this way I have implemented my model. These are the ABC waveforms. So, the summary part. From the result, we can see the response of motor at different speed and different load. But we can also see that space vector PWM voltage source inverter fed induction motor gives better result in form of less speed fluctuation, and torque ripple is also less compared to sinusoidal pulse width modulation. Now coming to performance, also analysis of PWM based PSI fed induction motor. The total harmonic distortion analysis of both SB sinusoidal PWM and space vector PWM fed induction motor is calculated through FFT analysis that I haven't shown here. So this way I have did the model. Thank you.
Any questions from participants?
So I guess no questions from participants. So thank you.
Thank you,
Thank you
Ananya.
so much for having me here.
Thank you, Ananya, for the session. Thank you very much. Next section will start by 5:45 p.m. Thank you.